Hi, in this video we are going to talk about shortest path algorithms focusing on Dijkstra's algorithm. So let's get started. Dijkstra's algorithm and Bellman-Ford algorithm, these are the two main techniques for finding shortest path in a graph, whether this graph is directed or undirected. So Dijkstra's can handle positive edge weights, while Bellman-Ford can have negative weights as well. And that's why Bellman-Ford algorithm is a bit slower, but we can do a lot more with the help of Bellman-Ford. For example, if we want to find arbitrage situation in Forex stock market, then we can construct an algorithm with the help of Bellman-Ford, and we can find these kinds of arbitrage situation. And if I'm not sure whether you are familiar with algorithmic trading, but lots of techniques as far as high frequency trading is concerned relies heavily on graph algorithms, and these kinds of algorithms such as shortest path algorithm and Bellman-Ford algorithm. And out there are lots of applications of shortest path, because we know for certain that these algorithms works fine. So we try to reduce lots of problems so that we can solve it with the help of Dijkstra's algorithm or Bellman-Ford algorithm. And one example is the knapsack problem. I'm not sure whether you are familiar with it. If you are not, there's lots of good articles, for example, in Wikipedia. This is an integer programming example, and there are two solutions for this problem. And one solution is the one that we try to construct a graph, and we can find a solution that with the help of a Dijkstra shortest path algorithm. So we know for certain that it works fine and it's very efficient, so that's why it's important. So, such as GPS, routing protocols on web or stock market, there's a lot of applications. As far as the type complexities are concerned, Dijkstra's algorithm has a ordo v times log v plus e, where the v denotes the number of vertices in our graph and the e denotes the number of edges in our graph. On the other hand, the Bellman-Ford running time is ordo v times v, v squared, which is a bit slower. Of course, the v denotes the number of vertices in our graph. It's a bit slower, but as I said earlier, Bellman-Ford algorithm is a general one, so we can use it for lots of applications, such as stock market, for example. Dijkstra's algorithm is a greedy one. It tries to find a global optimum with the help of local minimum. And an appropriate data structure for this is the heap data structure, or we could use arrays, but heaps are much more popular. And for example, binary heaps are good, but a well-implemented Fibonacci is the winner. So with the help of Fibonacci, we can make sure that the Dijkstra's algorithm will run very fast. So yeah, let's consider a situation when we have vertices such as A, B, C, D, H, F, G, and so on, and it is a directed graph. So there's an edge between each of these nodes and vertices with a given weight, and this weight is going to represent the cost. I mean, the units we have to, if we want to go, for example, from A to B, it's going to cost 5 units. I'm not sure, but it can be, for example, the price of gasoline. It can be a distance, for example, 5 meters or whatever. So we have to select a start vertex, and it's going to be the A. And Dijkstra's algorithms works as the following. We are going to visit all of its neighbors. And we are going to maintain a heap, and we are going to store the minimum distances on this heap according to the mean distance of each node. So here we come to the conclusion that we can go from A to B, and it's going to cost us 5 units. And that's why, if we consider that here in the beginning we initialize each of the nodes to be infinity, it denotes that it is infinitely distant away from where we are standing at the A position, because we don't know how far it is. That's why we denote it with plus infinity. So here, after we visiting the neighbors, we came to the conclusion that the B, for example, we have to it costs 5 units to get there, and that's why we updated the B accordingly, because 5 is less than infinity. It takes 8 units to get from A to H, and that's why we updated the H to be 8 instead of infinity. We try to minimize the mean distance, of course, that's the purpose. From A to E, it's going to cost 9, so we update the E from infinity to 9. And our heap is containing these mean distances for the B, for the H, and for the E. So 5, 8, and 9. And we go to the next vertex that has the less value. So the mean distance is the minimum. And we have 5, 8, and 9. So we go to the 5, which is the B. And consider this A vertex visited. So we are not going to get back here anymore. And we are going to iterating our algorithms in the same manner. So we are going to visit our neighbors. We come to the conclusion that we can get from B to D with the cost of 15, but we have already have a cost 5. This is the mean distance. So in order to get from A to D via B, we can get from A to B with the cost of 5, and from B to D with the cost of 15. So if you want to get from A to D, it's going to cost us 20. So we are going to update, and the D is going to assign a value 20. If you want to get from B to C, it is going to be 17, because 12 plus 5. And here it is the tricky part, because we see that from A we can get to H directly from A to H, and it's going to cost us 8. But we can go with the half of vertex B. So we go from A to B, it's going to cost us 5. Then we can go from B to H, which is another 4 unit. 5 plus 4 is going to be 9, and 9 is greater than 8, so we are not. It is not a good solution. If you want to get from A to H, it is a bad path if we would take A to B and B to H, because it costs 9. And the direct route from A to H is equal to 8. So we are not going to update the H. Then our heap is going to contain the 20, the 17, the 8, and the 9. And we go to the minimum node, and it's going to be H. And we consider the B sorted. So from H we can go to C and F, so we visit each of its neighbors, and we come to the conclusion that it takes minimum 8 units to get from H from the starting node, and another 7 to get from H to C. So that's why it's going to be 15. And in the previous, if you can see that here the C has the value 17, but we keep iterating, and if we find a shorter path, we keep updating our vertices accordingly. So here 15 is smaller than 17, and that's why we are going to update the value, and this value is going to represent the mean distance from the start vertex, which is A, to the given node, which is, for example, here is C. We can go from H to F, this is the other neighbor, and it is going to cost us 14. Why 14? Because we have to, it's going to cost a minimum 8 to get from the start vertex to H, and there's another edge with weight 6. 6 plus 8 is equal to 14. So we consider it visited, and because we jump to the next smallest vertex, it is going to be E, and going to visit each of its neighbors. And we can go back to H. It is not a good solution because 9 plus 5 is equal to 14, and we have already has a mean distance 8, so we are not going to update it. But as you can see, the F is going to decrease because there's a shorter path. We can get from the shortest path is to go from A to E and E to F. It is equal to 13 as far as costs are concerned. And we can get to G with the cost 29. Why 29? Because we go from A to E, it is 9, and from E to G, which is 20. 20 plus 9 is 29. We keep iterating again, and the next vertex is going to be f. Why f? Because f has the minimum value, and our heap is going to store these, and we can get the minimum value. So 13, and we are going to visit each of its nodes, and we come to the conclusion that there's even a shortest path from f to c. I mean from the start vertex, which is a, to c, with the half of f. So we can go through this f, and we update the minimum distances accordingly. Then we go to c and visit its neighbors accordingly. Then the d, because 17 is smaller than 25, and we are going to update if necessary. And the last node is g. So with the half of this, we are going to store for each node, A, B, C, D, H, F, we are going to store another vertex or another node. This is called the predecessor, and the predecessor is going to point to the previous node in the shortest path. And with the half of this, we can construct what is called the shortest path tree. And why is it good? Because we just have to calculate it once, and then we can reuse it as many times as we want. And if you use GPS, this is what happens in the background. It is going to calculate the shortest path tree in a given distance, not to the whole world for all of the cities and all of the countries in the world. But if you are sitting, for example, in Hungary, as I do, it is going to calculate in a short distance. It's going to construct the shortest path tree. And if we want to get, for example, from A to B, we see with the half of the shortest path tree that we can do it with a cost of 5 from directly A to B. If we want to go to C, it is not a good solution to go from A to B and B to C, because it's not the optimal solution. We should go from A to E, E to F, F to C, and this is going to be the shortest path from A to C. If we want to go, for example, from A to the G, then we have to go from A to E, E to F, F to C, and C to G. And the minimum cost and the optimal cost will be 25. There is no other shortest path that would give us a better result. So this is how Dijkstra's algorithm works in the background, and I think it's a very, very beautiful and very, very useful algorithm. So thanks for watching.